Hey everybody, in this video I'm going to show you how to do a shortcut for determining the electron configurations of all the elements. And I'm going to talk a little bit about about helium and the noble gases. So let's spend a little bit of time doing this. Now, what ends up happening is there's two different types of electrons. There are valence electrons and then there are core electrons. The valence electrons are by far the most important ones, and they're the outermost electrons. They're the ones that are most likely to be transferred or have chemistry done to them in an element. So if I bring up a picture of an element, and again, I think I'm going to use the Bohr model because that's a little easier to see, even though it is inaccurate. So here's the nucleus, and then we have, in the first energy level, or the first shell, okay, we can have 2 electrons. Okay. Now we can go out to the next energy level, in the second energy level, and that's n equals 2. And in that energy level, we can have 8 electrons. And now I'm just going to go out to the third, but let's say we stop at the third. Let's say that we are talking about magnesium or aluminum. Doesn't really matter, but if we're talking about magnesium, magnesium is going to have 2 electrons, okay? And so that's when n equals 3. That's the third energy level. Now, this is why this kind of makes sense, is that these electrons, these outermost electrons here, these are the ones that can be easily transferred. These are the valence electrons, okay? Now, if those are the valence electrons, everything else, all of these guys, these are what we call the core electrons. Sometimes some old-time books or something, sometimes you'll hear them called the kernel electrons. Okay, but the valence electrons are the ones that are very easily moved around, lost, and electrons are also easily moved into what we call the valence, the outermost shell. And so that idea of valence electrons is important. Now, how can we easily determine what the valence electrons are? Well, the periodic table is set up very well for us to do all these crazy things. Okay, so if we have an element like sodium, okay, sodium has 11 electrons. And why don't we take a minute to draw its electron configuration, okay, or to write it down. If you're good, you can do it without, while I'm sitting here stalling. If not, you can pause the video and try it. And if you don't know that, then we can do it together. But so what we're going to do is we're going to go 1s2, right? 1s2, 2s2, 2p6, 3s1. Okay, that gives us the 2, 4, 10, 11 electrons that we need. And so that's the ground state electron configuration of sodium. Now, if we notice, this is the outermost electrons. These are the valence electrons. Okay, well, in this case, there's just one of them, so that's the valence electron. Now, what about these interior 10 electrons? Well, let's compare that. Let's do the electron configuration of, let's say, silicon. Silicon has 14 electrons, and so that's going to be 1s2, 2s2, 2p6, 3s2, 3p2. Okay. Now, the outermost electrons are still this. The valence electrons are the ones in the outermost shell. So the outermost shell is the third shell, the third energy level. But notice here, even though they're different elements, they're on the same row in the periodic table, and notice that their core electron configuration hasn't changed. Well, that leads us to an easy shortcut. What element has the electron configuration of 1s2, 2s2, 2p6? Well, that element is neon. Okay, so what we can do is we can shortcut these, or any element, by symbolizing the core electrons using the noble gas that is previous to it by atomic number. So if we look at sodium, sodium is atomic number 11. What is its previous noble gas by atomic number? Well, it happens to be neon. So what we're going to do is we are going to write neon in brackets, and that represents the 10 core electrons. And now we're going to then say, well, let's go here to sodium, which is in the 3, and then it's on the S side, so 3s1. So that still represents all the electrons, but we've shortcutted it so that we don't have to worry about the core electrons. The valence electrons are by far and away the most important electrons in an atom. Now, we can do the same thing with silicon. Okay, silicon is number 14, it has 14 electrons. What is the noble gas previous to it by atomic number? Well, 14, the previous noble gas is 10. And so that means neon. But now where are we going to start? So that's 10 electrons, and now we're going to go to 3s2, 3p2. Okay? That's the noble gas configuration. Now, I hear students say this all the time. Well, you know, it's not much of a shortcut. Well, guess what? Let's show you the power of doing noble gas configurations and why it is a shortcut. Okay, let's do the electron configuration of actinium, AC. AC has 89 electrons, okay, and it's right here. Now, what would you rather do? Start with 1s2, 2s2, 2p6. And I get it. Some people really enjoy that because there's a pattern to it and it makes sense and the periodic table kind of falls out and stuff like that. But, you know, let's do the shortcut because I don't think that it makes a lot of sense to go through the whole thing. So what is the previous noble gas by atomic number? Notice I keep saying by atomic number. I don't want you to pick the closest noble gas. I want you to pick the previous noble gas. So 89, we go back, 88, 87, 86. So that noble gas is radon, and we put it in square brackets. And now we have put in all 86 of those electrons just by writing that. So now where do we start? Well, radon, and now we're in 7. So we go 7, and then this is the S side, 7s2, and down here is 5f1. Okay? So that shortcut is powerful. Now, the last thing that I think I need to mention, well, the second to last thing I need to mention, is what if we are given a noble gas to write the electron configuration of? Okay? What if we have a noble gas and we want to write that electron configuration? Okay, so let's go to krypton. Okay, now if we're going to do krypton, a lot of students will take those 36 electrons and they will go, well, it's krypton, and they put it in square brackets. That is not correct because even the noble gases have to have valence electrons that can do stuff. So what we do is we go to the previous noble gas to krypton, which is right above it, which is argon, and then we fill in the valence. Okay, so 18. So now we're down here to this row. So we go to 4s2, 3d10, right, all the way across, and then to here. So then it's 4p6. Okay, so that's the way we do the noble gases. Now, the last thing, this is really the last thing that I want to make sure that you understand is the noble gases are very, very stable. Electrons don't want to react in noble gases because they have a filled outer valence. So if we look at this, let's see, how many electrons are in the outermost energy level? Well, let's see, here's 2 and 6, that's 8. 8 electrons is actually what elements want to have. Elements want to have 8 electrons in their outermost shell. As soon as they get 8 electrons, they don't really react. And so what happens with neon and argon and krypton and xenon and radon is that since their outer shell is filled, they don't react, and that's what makes them noble. That's what makes them inert gases. Okay? And now helium is over here too, because helium is a special case but follows the chemical principle and not the mathematical pattern. Okay, let's look at helium because the chemical principle is highlighted by helium. What makes these gases, neon down to radon, stable? We don't use UUO because it's not confirmed and it's just not there. It's on the periodic table, but it's not something that we play around with. So from neon down to radon, the reason why we say that those are stables is because it has a full outer shell. So when we look at something like neon, it's 1s2, 2s2, 2p6. It has 8 electrons in its outer shell. Same with argon. It's 3s2, 3p6. And then same with krypton. So it has a full outer shell. Now, let's look at helium. Helium only has the 1s's. How many electrons can we put in the 1s's? We can only put 2 electrons in the 1s's. So the chemical principle is that if it has a full outer shell, it is stable and it is a noble gas. So helium fits the rule and is put over here on the periodic table because helium is inert. It has a full outer shell. It doesn't react. It doesn't want to give up its electrons. That's why it's not over here. These elements react. Magnesium, calcium, strontium, they all react. They even react with water to form bases, and that's a pretty crazy reaction. And so their whole outer shell isn't filled. Here the outer shell is 2, and so it's 2s, but there's a whole bunch of p's. There's no electrons in the p's, so there's space in there. Helium is stable because its whole outer shell is full. The outer shell is just an s, has s electrons or s orbitals, so those 2 electrons fill the outer shell, and that's why helium is put over here. Actually, you will see some periodic tables that will put helium here and here. You'll see it in both places because it matches the pattern of the periodic table. Okay, so that's it. That's how we talk about shortcuts in the periodic table.